everyone. My name is Nehul Vias. I'm a Director of Analytics Consulting and leader of the Tableau Solution Group here at AVAP. We're so very appreciative of the opportunity to present to you all today, and certainly appreciative of your attendance and engagement throughout this session. Before we dig into our topic, I'd like to provide just a quick overview of AVAP and share a little bit about ourselves. AVAP is a cross-platform, industry-specialized global IT advisory and management consulting firm. Our span of consulting and technology resources enable us to build for the future faster and better than before, combining a massive breadth of experienced consultants across several consulting practice areas with the ability to support clients across multiple sectors and industries. Our analytics offerings span the entire data value chain, from organizational data strategy, where we help clients develop a comprehensive roadmap to their analytics and technology investments, rapid ROI, where the focus is on driving adoption and utilization of an analytics capability across an organization's footprint, and continuous value, to focus on sustained and scalable growth. These three pillars are complemented through our ability to execute engagements from robust and transformative solution delivery, supporting enterprise data initiatives, Tableau dashboarding quick starts, Tableau technical health checks with a focus on the infrastructure, setup and configuration of the Tableau environment, and we even serve as a managed services provider to some of our clients to fully host their Tableau capability, accompanied with full service operational SLAs and hands-on maintenance. Before we get into introductions for our presenters today, I wanted to quickly mention that if you do have a question at any time during the presentation, please do either use the QA box at the bottom of your screen or the chat function. We will certainly make sure to address your questions in time. This session will also be available on demand within 2 business days of its recording. Now it's my distinct pleasure to welcome our 2 presenters today, Will Gilliland, Senior Analyst in our Data and Analytics capability, and Aaron Sheehan, Senior Analyst in our Data and Analytics capability. Welcome, both of you. I know we've got a spectacular topic here today. I don't want to belabor introductions anymore, so I'm going to hand the ball off to you, Will. The floor is yours, sir.
Hey, everyone. It's nice to be chatting with you all today. Today, we're going to talk about how Aaron and I were able to successfully ingest and derive data from public data sources and then visualize them in Tableau. So to first give a good overview of our project, the Office and Budget and Management for a state government wanted to replace manual Excel graphs displaying economic metrics in a weekly report with automated Tableau dashboards. These models leverage public data sources to drive economic insights about state citizens, businesses, and cities in an efficient manner. So to give a quick overview of our solution, Tableau's ability to connect to a wide range of ETL tools and multi-connection data sources provide us the ability to automate and visualize these public-facing data sources. Public-facing data sources can be used to drive insights about your audience in both the public and private sector. A quick overview of the technologies we used in this project were Tableau Enterprise, Desktop and Server, Alteryx, which is an ETL tool, Cloudera's whole suite of capabilities, and then StreamSets, which is a data pipeline and ingestion tool. So to give a quick overview of our development approach for this project, after requirements gathering, we mocked up data from the public data sources in Excel and built out first drafts for the visualizations. Once the data was ingested to our data warehouse, onboarded and transformed according to their requirements, we were able to easily replace the data sources, which allowed us to quickly iterate through Tableau development and worked on multiple dashboards in parallel. So for an overview of the Tableau dashboards, in total, we built 19 dashboards out, and data sources were all ingested into a single centralized data platform with little to no manual work. The dashboards displayed economic trends, year-over-year comparisons with a focus on pre-pandemic metrics for consumer and industry activity. The dashboards were refreshed on a weekly to monthly basis using a scheduling tool. We ingested data sources from 9 public sources, 7 of these being automated and 2 requiring a manual file drop. So to talk about some lessons and learnings, our successful change request and requirement documentation allowed for quickly identifying pain points and prioritizing requirements. Hundreds of requirements and change requests were successfully completed during the project's lifespan. We iterated through around 280 total requirements and change requests. Common pain points included overlapping change requests, technology limitations, and a lack of control over the source data. An example of an overlapping change request we came across was a request to do percent change comparisons for retail sales by industries using 2019 as a baseline. This was so they could do a comparison to pre-pandemic metrics. The year-over-year comparisons were the initial requirement, but the stakeholder wanted to display comparisons pre-pandemic times, so we ended up doing ETL transformations to display both in the visualizations, and Tableau's sheet swapping capabilities were extremely dynamic in performing and showing these visualizations. The technology limitations included limitations on API calls and our data ingestion tools, and also utilizing a 4x4 retail calendar for daily year-over-year comparisons to avoid outliers in the data when it came to holidays. We were not able to control source data for the public data sources if the website changed its date formats or stopped publishing data. So now to do a project deep dive. So these are the three use cases we're going to talk about today. In this visualization, you can see the data sources are broken up by the methodology of how the data was ingested, and lines denote whether it is an automated ingestion process or contains some manual work. Once the data is ingested, it is transformed and published to Tableau server, the Tableau server's agency site. The dashboards were then created in desktop and were published to server to be viewed by the stakeholders. So now we're going to talk about one of the first use case. So the data for this dashboard was actually OpenTable dinner reservations on OpenTable, the app's public-facing website. So the dashboards display seated diners data downloaded from OpenTable's public data sets. The metrics detail the daily and monthly percent changes in seated diners from the current year to the same day and week in 2019 pre-pandemic. The dashboards focus on states versus the US, and then various cities and geographic locations. As you can see on the right, the data included increasing columns, which create difficulties in building a structured Hive table in Cloudera. OpenTable also did not have a public API to ingest the source data. We also ran into a pain point where OpenTable changed the formats of their dates multiple times. We landed on a solution where the stakeholder would download the data to a CSV once a month and upload the file to Hadoop's distributed file system, or HDFS, which is a Java-based file system for storing large volumes of data. We then used an ETL tool that works wonderfully with Tableau called Alteryx to transpose the date columns to rows and create regex match functions, which looked at potential date formats, returning the correct match and transforming it to a set format easily ingestible by Tableau. So now we're going to talk about, Aaron's going to talk about the data ingestion process for OpenTable.
So we were able to enhance our OpenTable ingestion by using a data engineering platform called StreamSets. According to their website, StreamSets is dedicated to building the smart data pipelines needed to power data ops across hybrid and multi-cloud architectures. So with StreamSets, we can create, execute, and operate continuous data flows that connect to various parts of our data infrastructure, including different sources, processors, and targets. So if you're familiar with Alteryx, StreamSets is very similar in that you can drag and connect different modules together and then configure them how you need. So it's basically code-free, although you can code in certain places if you want to. The difference with StreamSets is that it's used for data ingestion for big data pipelines, and Alteryx's strength is more in data analytics. So for this use case, the OpenTable file was downloaded and manually dropped into a Hadoop file system or HDFS directory. There's no formalized drop time. It was just dropped at random, and the file name was always inconsistent. And before it could go to the next steps into Alteryx, the file had to be moved into an Alteryx accessible HDFS location and be renamed to have a consistent file name for it to look for. So the StreamSets pipeline pictured here was created to be constantly running or streaming, waiting for a new file event to be triggered by the file being dropped in the HDFS location, which is configured in the first module. When a new file event occurs, the shell script module relocates and renames the file so it's ready for a subsequent Alteryx job. So overall, this is just a very basic StreamSets pipeline and really doesn't do justice for what the platform is capable of. So the next part of our project, we were able to utilize more of its capabilities. So I'll pass it over to Will to introduce what we did next.
Thanks, Aaron. So for this next use case, we were able to ingest data from the Bureau of Labor Statistics and the U.S. Census Bureau. These Tableau dashboards displayed employment and retail data ingested from these public data sets, and metrics detail the daily and monthly percent changes in retail sales and private employee wages/hours worked. Dashboards focus on states versus the US, Midwestern metro areas, and US states. The data for these dashboards were ingested using web APIs and displayed various metrics around hours earnings, hours worked, and retail sales metrics across various geographic locations. Tableau's parameter and mapping capabilities made these views extremely dynamic and functional across a variety of measures. Some limitations we ran into was a limit on API calls, which Aaron will speak on. We also required mapping to inflation data manually uploaded by the stakeholder and FIPS code mapping for state names, which we were able to join to our data sets using Tableau's multi-connection data source capabilities. Some ETL transformations that were done for this use case using Alteryx were to combine country and state level data, as well as breaking up series and industry codes for mapping specific measures and locations. Now, Aaron's going to talk a little bit more about the data ingestion process for these.
So the BLS and census data are two different data sets that require two separate ingestion processes, but both are very similar. Our end goal for the ingestion is to take public data from an API call, like we'll talk about, and then deliver it to a table in our Hive data warehouse, stored in our Hadoop ecosystem, so it could be easily accessed, again, then next by Alteryx, and then make its way to Tableau dashboards. So here's an overview of the BLS and census data ingestion. In the open table solution, we really only had the last stream set step. However, during development, some functionality limitations to stream sets were exposed that allowed us to utilize other technologies to enhance stream sets even further. So the first tool that we used in the process is Control-M, which is a user-friendly scheduler that will then schedule a special Python code for stream sets, which is called StreamSets SDK. And then StreamSets SDK Python uses a library to connect to StreamSets environment and can interact with it programmatically. So we use it to start and stop StreamSets pipeline jobs. And then within the job in StreamSets itself, it connects to the public API URL and processes the data to the Hive table destination. So this is just a very high overview of the order that the process goes in. It's running when it runs every day. I'll dive deeper into each one of these steps, but I will do it in reverse order as it was the order taken during development. And this way it's a lot easier to showcase the discovery of the technology limitations and then the solutions that were taken to fix them. First, I'll take you all the way back to what the raw data for BLS and census is kind of looking like. They both come in two different flavors of JSON files. So there's a multi-dimensional array and a JSON object. So you can kind of look and see they have slightly different syntax. For the US census data, the requirement is we wanted to collect the monthly retail sales data from 1992 until the current year. However, when we submit the API URL, we are only allowed to use 1 year at a time as a parameter. So in order to get all the data, we would need almost 30 different API calls. And then for the BLS data, instead of year, we want the data for about 1,000 different data series IDs. So luckily we don't have to do 1,000 different data or API calls. Instead, we can include a list of up to 50 series IDs at a time as a parameter. So in this case, we would only need about 20 API calls in order to get all of the data. So here we have the StreamSets pipelines used for census. And the BLS pipeline looks slightly different because it processes its JSON file type a little bit differently, but the overall structure looks the same. The pipelines start with an HTTP client module. In the screenshot, it's currently selected so you can see a little bit of the configuration where the public API URL is specified. This is the origin that is what's getting the source data. From there, a JSON evaluator, field renamer, and field splitter are all configured to manipulate the JSON file into the desired format that we need it in, and just get through all that messy JSON formatting. And then based on certain criteria, it gets split into two different tables that both then truncate and reload the Hive table. with the Hive metadata and metastore modules at the end there. While this pipeline has great functionality, the HTTP client origin only allows one API call at a time. And if you remember from earlier, BLS and Census both require like 20 to 30 each. And unfortunately, a limitation that was discovered to StreamSets is that it lacks the ability to loop through a list of different API calls, unless if we wanted to create about like 20 to 30 separate individual pipelines, which is just too much clutter. So in order to increase the functionality, we utilize StreamSets SDK Python code. And again, according to the StreamSets website, StreamSets SDK allows developers to automate the creation and execution of data flow pipelines in StreamSets execution engines and the StreamSets environment. So overall, we can just use SDK allows us to use a more programmatic approach to expand the platform's capabilities. In the StreamSets environment, we publish the pipeline to become a job template. And a job template allows us to spawn different job instances off of it with specified parameters to use in the job. So in our case, we can parameterize year, like the different years for census in the API call, and then the list of series IDs for the BLS data. In order to have, a different API call each time, we could just spawn a bunch of jobs with all these different parameters. So on the slide, I have a pseudocode that kind of takes you through a very high-level overview of the programmatic approach for the census data. So first, we of course have to get the StreamSets SDK library imported, so we're able to connect to StreamSets itself, and then retrieve the job template with the job template ID. And then I initialize a start year and a current year, and I get current year based off today's date with a function, so it'd say like 2021. And then we loop through each year from 1992 to 2021, which would be the current year, right? And we use year as a parameter, and then we submit it into the job template to spawn a job, and then it gets used in the API call in StreamSets. So then the code can programmatically wait for the job to be in the completion status, and then it gets deleted to prevent all this clutter from all these spawn jobs being created. And then after that's all done, the next year, of course, will get started, and then we just keep going through the loop. And the code for BLS is very similar, once again, just slightly different because we just have to loop through lists of series IDs, but like the process is very similar. So next we need to schedule this Python code to be kicked off. So to schedule the StreamSets SDK Python code to run every day, we use the Control-M scheduler. And according to their website, Control-M is used to monitor batch schedules from different application groups and multiple servers to reduce the resource manual work. So ultimately, we use Control-M as a centralized interface to monitor and manage batch processes within our organization. The perk of it is that it's very user-friendly. Jobs are scheduled through modules that we can drag and drop into organized folders, and then we can order the jobs into a desired schedule. So for this use case, we configured the module's general properties with like the command that we wanted to use, like to run the Python code, and then what user we wanted to run in, etc. There's a screenshot then of the module scheduling properties, which is configured to run the command with a certain user every day between 5:15 and 6:15 a.m. Other properties we can configure within the properties are a customizable email notification that can be sent to us upon the completion or the failure of a job. So overall, Control-M is super interactive in that we can visually assess what jobs have completed, as indicated by a red check mark, as you can see in one of those screenshots. And then we can also see what has yet to run, like the gray hourglass, to indicate that it's waiting for its scheduled time to get set off. And then if it fails, the module will appear red, and then while it's running, it will be yellow. So it's super easy to interpret. So just to bring it all back together in the correct order of events, we have a Control-M scheduler that submits the command to start the StreamSets SDK Python code. And within the StreamSets SDK Python code, we loop through a list of years or series IDs to use as parameters to spawn jobs from a job template. It'll wait for the job to complete, then delete it after the job gets all done. But within the StreamSets Python job itself, the job parameter or the parameter submitted, your series ID is used to call a specific API URL. The data is ingested and then hits our target Hive table. So in the end, we're able to engage multiple technologies to enhance each other in the data ingestion and allow easier data access for subsequent data processing in Alteryx and eventually Tableau.
So to give a quick project recap, so this is similar to the functional diagram that we looked at earlier, but this encompasses all of the data sources that we were able to ingest for this project, and then also the analytics platforms and the Tableau Enterprise, and then eventually on the right, you can see our business users were able to access these dashboards. So just to give a quick overview of a couple of the other cool public-facing data sources we were able to ingest data from Realtor.com to look at different housing median listing prices and housing demand across a variety of markets. We were able to ingest data from a website called Opportunity Insights, which is hosted on GitHub, and we were able to look at Google mobility data, which is looking at how much time people were spending at home or away from home, which was a really good indicator of economic activity in the face of the pandemic, as well as job postings. So, average job postings across a variety of geographic locations, small business revenue on average across a lot of locations. So as you can see, there's lots of public-facing data that's out there that we were able to access and then turn into different dashboards using Tableau, and then our end user was able to drive lots of interesting insights, and those insights can help drive different policies, across the state. So something that is very actionable is we were able to gather data about different eviction filings across the state, and as you know, during the pandemic, lots of states implemented eviction moratoriums where this was drastically impacting the amount of eviction filings across different locations as well. So lastly, let's talk about some insights gained. So Tableau's mapping functionality allowed us to visualize at the census tract level for eviction filings in certain districts across different states up to whole countries. So this is an insight that we were able to gain off of Tableau's functionality that previously in Excel there was no reporting for. So there was a lot of cool things we were able to do with mapping in Tableau that previously our stakeholder was not able to use at all. Tableau's parameters and sheet swapping capabilities allowed for a cleaner, more efficient visualization of all of the data. Tableau's ability to connect to multiple analytics tools and platforms cut down on the data cleansing and development time. And weekly economic reporting for the client was cut down from a multi-day development process to approximately a single hour per week. Now we'll be happy to take some Q&A.
I'm amazed at how well you two articulated such a robust solution and did it so elegantly. I gotta ask you, when you were architecting this, how did you a la carte these respective tools? I heard Control-M, StreamSets, a little bit of Python in there, obviously Tableau. I mean, walk me through just quickly the thought process on bridging the solution with these essentially disparate tools and how seamlessly everything kind of integrated together. Well,
Yep.
walk me through some of that.
So I think the main thing was we had a great team of collaborators and stakeholders, and especially project managers that knew how to efficiently gather requirements from the stakeholder and then translate that into all the capabilities of our team. And so we could easily come up with which technologies will work the best in these specific solutions, and then whether or not something might be redundant or something was actually necessary, and then working together as a cross-functional team to outline a plan and execute on that plan in sprints throughout the project.
Yeah, that's fantastic. And Aaron, I mean, I know you deal with a tremendous amount of data, and architecting such a solution, as you're talking to an end user like me, one, you did a fantastic job, again, breaking out the crayons to make it easily understood. But walk me through, I guess, just in the context of requirements and design, those conversations that you're having with a client to help them understand the building blocks to get to the end goal. Again, sometimes people look at very interactive, intuitive dashboards on the front end and lose sight of the journey that gets them there, right, with the data. Walk me through some of that experience that you have with clients as you're in the bowels, in the trenches of data and curating it and building pipelines to get them to the end goal.
Yeah, I mean, I think you start with such a simple idea that like, okay, we're just going to do a simple stream sets pipeline. It's like that's your, method of choice to build some sort of ingestion process. But yeah, I mean, there's, always some sort of adversity that comes along your way where it's like, I don't think this can do what we need it to do. So yeah, just being able to find and utilize more technologies in addition to that, I think really goes a long way.
Yeah. And I have to imagine that those tools that you're mentioning, maybe not necessarily Python, but certainly I know Alteryx, StreamSets as well, these are user-friendly tools from a visual perspective, right? So it's not necessarily a fully newbie in the data world just jumps in and starts banging out, I guess, workflows or transformation efforts with these. But it seems like they are essentially made for a little bit of self-service, right? So again, you guys really did a great job articulating an elegant solution in a well coordinated manner with all of these, again, capabilities, tools that got to the end goal. I have to imagine that other people would have the same opportunity to do the same, right? Just with a little bit of wherewithal and getting themselves in the journey. I guess last question I have for both of you, in your young careers, what would be your piece of advice for people that wanted to get into the data space and start assimilating and working themselves into these tools? Any just pieces of advice?
Yep. So I would say going off of that, biggest thing is to ask questions, but then I think that the important questions come with taking attempts. So learning how to fail, and I think that's extremely important when you're learning a tool like even Tableau, Alteryx, or StreamSets, trying your best to get to an end goal and then running into bottlenecks along the way, and then asking the right questions to figure out those solutions. That will help you, gain experience faster, learn faster, and develop and eventually, hopefully, become an expert in these tools.
I'd have to imagine too, Aaron, and maybe this is more in your world, dealing with a lot of data again, the nature of prototyping, the nature of iterative development, the nature of if you're going to fail, let's fail fast and then recalibrate our approach. I mean, is that fundamentally? Is it fundamentally a welcome thought to the development efforts for you, where you do have confidence that if you do fail, you can just go back to square one and start all over again?
Yeah, I feel like a lot of the time, the expectation is you're going to fail. I mean, it's very hard to get it right on the first try, unless if you've obviously done the process before. Yeah, I think, sometimes you spend a lot more time than you anticipate. I think this project actually was one that just took a while, that we were like, why are there so many issues going on? And, eventually we perfected it with these different technologies. But yeah, I definitely think failure is anticipated.
Yeah. And last question, I mean, you mentioned OpenTable as part of, one of the use cases, Realtor.com. How do you grab copious amounts of data from these organizations? Is there a UI function that can get you a download of this data, or where did you find that publicly available data?
Yep. So for this project specifically, a lot of this data had parameters in which you could download the data from the websites in text file formats, where previously the end user had websites that they wanted to that they downloaded data from and were building just Excel graphs and just different insights from, but they knew like if we were able to push this to a data platform, we could gain a lot more insight from this data, especially when it came to a lot of the geographical data that we were able to access. So for example, for Realtor.com, a lot of the data was hosted on GitHub, and there are git clone commands you can run on their servers in order to pull in that data to our data analytics platform. And then for something like the U.S. Census Bureau, Aaron was able to use their API to also ingest that data. So there's a myriad of different methodologies that our data engineers were very successful at pulling down, data from these websites. And then also, for an example like OpenTable, that was a manual download from their website and then an upload to our data warehouse where we were able to, use Alteryx and Tableau and do some cool visualizations.
I love it, guys. Aaron Sheehan, we'll go on to our bright young stars in our data analytics practice. Thanks so much for the time today. Awesome topic, awesome presentation. Thanks so much.
Yep, thank you guys.